So let's go ahead and get started. So the online quiz, I did want to point out one thing. It was pretty good. Most people did the math with kinetic energy fine, recognized the formula for potential energy, identified potential versus kinetic energies. One thing to highlight, remember, the force of friction times distance is called various things, either internal energy or energy dissipated. Sometimes certain books and people only refer to it as a work, which strictly speaking isn't correct. It's not a potential energy. It's not a potential energy because it is energy that will never go back into kinetic energy. So that's one way to think of this. Potential energies are energies that when you gain potential energy, at some point later it can be turned back into kinetic energy or to another potential energy. That's why it's the potential. It's the potential to move. Internal energy, energy from friction, is just basically turning into heat. That's why we did the example of rubbing our hands together. So anytime there's friction, friction is taking either potential or kinetic energy, or both, turning it into dissipated or internal energy or heat, something you're never going to use again. So that's why it's not a potential energy. So that was with that one. The other one I wanted to highlight, the other concept, notice the question asked which single piece of information is sufficient to calculate the height of the jump. And the force you leave the ground is not sufficient, right? The force, you need to know either how long or how far that force is acting, what distance it's acting over or how long it's acting for, to determine either the acceleration or the work or something else. The magnitude of the force itself is not enough to tell you how high you will jump. What matters is how long that force acts over or how much time. And that was why we had to introduce work. Work was force times displacement. And it was that whole thing together that told you about the energy you gained. Once you know the speed, right, we'll see that you can compare that to your mgh. The reason you don't need to know the mass is 1/2 mv squared equals mgh. The masses cancel out. So your mass does not come into how high you go. All that comes into how high you go is your speed. Questions on that? The final thing from the quiz was some of the general comments. And I just wanted to let you all know that there's lots of you in the same boat at this point in the course. It's hard to take everything we learn and put into one problem, keeping track of all the things we learn, still having this trouble deciphering language. And I could have put a lot of these quotes. And so that is one of the reasons when I teach this course, if you notice, I try and use 10th week for a little bit of review. And why you even have an exam the last day of 10th week, believe it or not, is so that by the time we get to that final on Wednesday, you get that little extra bit of time to kind of put this all together. Hopefully that'll help. I really, really like this one, because I couldn't have said it better. Whoops. Apparently I can't highlight it. Yeah, I can. OK? I don't really understand what is going on in class until I go back and watch the podcast again. That's perfect. It's very, very hard in a 50-minute physics lecture to understand everything I said. Okay? The best you can do is experience it. Right? It's kind of like let it wash over you. Do your best. But between watching the podcast, doing the problems, going to discussion section, coming to office hours, going to the tutorial, talking to your friends, saying, what just happened? You know, what did you get out of that last 50 minutes? That's where it'll come together. This is not a class you can survive in just by coming in and listening to lecture and then hoping you can do it. I said at the beginning, many of you probably didn't believe me. Now you do, because you're writing it on the quiz. So good job. Any questions there? So what are we going to do today? We're kind of going to approach energy conservation in 3 stages. So today, I'm going to do a whole bunch of what I consider the simple energy problem examples, and I'll tell you why I think they're simple. Tomorrow in discussion, you will do the hardest of the simple. So you won't do anything much more than what we did today, just kind of at the next slight level. And then Friday, in lecture, I will have do kind of what I think of as the hardest energy problems. Then next week, we go into collisions. But the big thing that you have to just keep in mind now is as soon as you recognize that energy might be relevant to the problem, you want to start keeping track of what's going on. And a great way to do that is the table, because our ultimate goal is that we're going to use work causes a change in energy. And if work is 0, the change in energy will be 0. And the change in energy is final minus initial. So what we need to know is the initial and the final energy. And in this class, there are only 4 energies we will deal with: kinetic energy, potential energy due to gravity, potential energy due to a spring, and energy dissipated, or what you might call the internal energy. That's from friction. And you add them all up, and you have the total energy initial. You add to that any work in the problem, and that'll equal the energy final. So this is why I say, at some level, energy problems are the easiest in this class. The concept of physically what is potential energy is very hard. But to use it if you just believe in it is very easy. And this really is a point where, I hate to say it, the starting point is just recognize that if you think energy is being used, there's 4 energies. Check for all of them. Apply E initial plus work equals E final. You will get one equation. It will have 1 or 2 unknowns. If it has 1 unknown, you're done, solve for it. If it has 2, figure out what else you need to do to find the other one. That's the process you're going to practice. After practicing enough, you'll start to get a better understanding of what these 4 energies are. And I'll try and help you with that. But this is a very mechanical part of the course. It's very much work through it. Now, let's review real quickly what those 4 energies are, right? Kinetic energy, any moving object has it. And it's just 1/2 mv squared. That's pretty easy. Potential energy due to gravity only occurs if you have a system with the Earth plus an object. Each object will have its own potential energy associated with the Earth. You need to select a point where the height is 0, and then the potential energy of gravity is given by mgh. Now, in all of these problems, ultimately the only thing that ever matters is the change in energy, because notice we always have an initial and a final. And the real fundamental formula is for the change in energy. But by picking a point where h equals 0, we can use a formula for the initial and the final energy. So that works. Potential energy due to a spring is whenever you have a spring. If you don't have a spring, you don't have that. Now, sometimes your spring is a rope that stretches that the problem says acts like a spring. Sometimes your spring is a mattress that you're sitting on that the problem says acts like a spring. Sometimes your spring is a bow in a bow and arrow that stretches and acts like a spring. And they will have to always give you a spring constant K. But the potential energy of the spring is 1/2 kx squared using x equilibrium as 0. So you have to know where the equilibrium position of the spring is and set it equal to 0. Now, again, this is because the change in potential energy of the spring is 1/2 kx final squared minus 1/2 k, whoops, forgot the k, kx initial squared. And the final one was our internal energy. This is always 0 initially. I mean, you can set it not to be 0 because the change is all that matters. And if you set it to some arbitrary number, things will still work out. But the easiest thing to set it to, since all that matters is the change, is 0 initially. And the final energy dissipated is the force of friction times the distance you move. So it only exists if friction, and in this case, kinetic friction, is in your system. So I would recommend keeping this, and this is on that 2-page formula sheet. Keep this with you at all times during the homework for the next week or two. And make sure this makes perfect sense to you. And you've got all of this. Any questions on our 4 energies? Yes?
Do we need to worry about something actually before the case? Just force of the spring, force of
So
negative K.
the force is negative kx. Yes, that matters. That tells you that the force is opposite where you're going. The potential energy is not negative 1/2 kx squared. The potential energy is 1/2 kx squared.
So we don't need to worry.
There is no minus sign there. If you go back and look, the work done by a spring has a minus sign because the force has a minus sign. But the potential energy is the opposite of the work, so it doesn't. Yeah?
Can you explain again why force of friction times distance doesn't equal potential energy?
It's not a potential energy. This is more, the name is less relevant. All you really need to know is that you've got 4 energies, 1/2 mv squared, mgh, 1/2 kx squared, and F force times d. Whether you call it a potential or not is an important concept that doesn't come up much in solving the problem. But the real reason is exactly this. It's never an energy that's around that you can use to generate one of these others. It's always showing up only in the final answer as in your objects as heat or vibrations or stuff breaking. And so what friction does is if you have any other initial energies, potential energy or kinetic energy, some of that always gets used up by friction or goes into friction in the final. And you'll see that when we do the problems. And you never get it back out. Other questions? Now, the final piece in all of this, remember, is since energy initial plus work equals energy final, all we did in chapter 7 to learn about work becomes relevant. What we're not going to do anymore, however, really, is worry about work done by a spring or work done by gravity, because we're always going to put it in our system and have the potential energy of the spring and gravity. If you ever find in a problem for the same spring or the same object, you do both work due to gravity and potential energy of gravity, you have done it wrong. Stop. But occasionally there are external forces, right? So work, 2 pieces. The force has to be external. And 2, if you remember, work is F dot delta x. So a force perpendicular to the displacement does no work. So there are 2 ways in which we will have no work done on our system. The first way is that there just are no forces. The second way is that our forces are perpendicular to our displacements. So if I look, and we'll come back to this, at my most general expression for energy, if I had all 4 energies in a problem, that's what I would have. And notice, right, it's all about nothing with a vector. It's about speed. It's about height. It's about position. And it's about distance traveled. Right? None of those are vectors. They're all scalars. And a fundamental clue that you're doing energy is that you know exactly the path the particle took. So if you watch all of our energy ones, there'll be things like something swinging on a rope. Notice the rope is setting the path it's going to go in. So we know the distance traveled because we know the path. We know its position or height or speed at various points because it's fixed on the path. The other key thing is we might be doing roller coasters and hills of various types. And again, you're told that the object is on a track the whole time. And so your motion's all known. Typically, if I go up a ramp and then I'm flying through the air, once I'm in the air, I'm probably switching over to using projectile motion, because now I'm not tied to a particular fixed path, track, or thing. So it's likely in that point to use a new thing, even though I have initial and final. And we'll reiterate this as we go later. But I wanted you to recognize that in all of these problems, we're going to end up with just one equation for each motion, and it will have scalars in it. Any questions on that? Excellent. We're going to go through a couple of example problems now and demos, but I'm going to show you another technique for organizing this concept as we do it. So what we're going to do, if you remember yesterday, or not yesterday, Monday, I had an object on a rope that I swung, and it came back and luckily did not hit me. And we're going to look at its motion, and we're going to consider kind of 3 points in the motion. And a good way to tell where it is that angle theta. It has some height above its lowest point, which we'll call h equals 0. And this length here, because we can do our geometry, is L cosine theta. Right, that's our general motion. I'll put up a particular problem in a moment, but what I wanted to do is for any motion, say we go from 1 to 2 or 2 to 3, what we're going to set up is an energy initial plus any work equals energy final. And we're going to ask how much kinetic energy is there, how much potential energy from gravity, how much potential energy from a spring, and how much energy dissipated. And we're going to make bar graphs. So the first thing I want to do is ask you a clicker question. We'll see what happens for the next one. And I may not count this one then, if we're still getting red lights. OK, 0. Now, here's the thing. Can anyone tell me why it's 0?
The ball doesn't move towards the center of the radius.
The ball what?
The ball never moves towards
The ball never moves towards the center of radius, so in our other language we call that the force is what relative to the displacement? Perpendicular. So the force is this way, and the displacement's that way. They're perpendicular, so the force of tension is perpendicular to delta x, so work is 0. So right here, I know my work is 0. I don't know why that erased. Now, when I start, if I'm going to just let go, how much kinetic energy do I have? If I'm just letting go of it, if it's not moving? 0. But I have some potential energy of gravity, because I called that h equals 0, so I have some mgh. Is there a spring in the problem? Nope, so there's none of that. Is there any energy dissipated at the beginning? No. If this is a frictionless pendulum, okay, when I'm down at the bottom, do I have kinetic energy? Yeah, I'm moving. It's swinging. I mean, I might not, but I probably do. Do I have any potential energy of gravity at the bottom? No. Do I have any springs? Nope, none showed up. Anything get dissipated? Nope, no friction. So, by my rule that E initial plus W has to equal E final, I immediately know this bar has to equal that bar. So this 1/2 mv squared is equal to that mgh. And graphically, I've got this and I'm done. Now, I'm going to make this like really messy and do one in blue. If I'm going all the way over to point 3, the beginning is the same, right? This is starting at 1. If I'm going over to point 3, I'm not sure what this is, but I know point 3 is the same height. So my P, potential energy of gravity, is mgh. Do I have anything left from this bar to give me kinetic energy? No, it's all in my potential. So this has to be 0. So for case 3, I automatically found out that as I swing all the way to the same height, I have 0 velocity. What if I swing back to where I started? What will my velocity be? 0. So in the demonstration on Monday, when I first did it, why did the can get knocked over, but I did not get hit? I had to have pushed it, right? The only way for that to have worked was there to actually have been some initial kinetic energy, and then there'd still be some when it comes back. And that's another way, another tool, these bars can help you to do things like that. Any questions on that? So again, now you see why we call it potential energy, because it switches to kinetic and then back to potential. If it had been dissipated, it's gone for good. It can't come back. Any questions? So now let's actually look at a problem. Okay, so let's suppose you start with the pendulum 45 degrees from the vertical. You let it go, and it swings down, so it's only 30 degrees from the vertical. And you want to know what is its speed at that point. This is what I call a very simple, quick conservation of energy problem. This is actually the type of problem, maybe not this one because I have angles in it, but this one I could. Something like this could be a short answer question on the exam. And the basic thing you're going to do is what we just did in this case. Okay? Whoops. You'll set up your initial, and you'll set up your final. I'm actually going to still call, when it's at the bottom, h equals 0. I could call the second place in the swing h equals 0. You'll see why for this case I'm calling the bottom. So I'm going to look at kind of the general situation of here's L that it's swinging with. Here's an angle theta. So for any given angle theta, my height from the bottom, right, is the whole height, L, minus this piece, L cosine theta. So at the beginning, what makes this one just slightly harder than the easiest energy conservation is I have to figure out, I was given angle, I'm going to use mgh, I already wrote that in the previous slide. So I need to know what the height is in terms of the angle. So every now and then, you're going to have to do that, where you're given, one of the things you know you're going to want to do is the potential energy of gravity, and you're given h in terms of theta, so you need a formula for it. And that'll just come from doing your trig, usually. You'll be at the top of a ramp, and it'll give you the height of the ramp, then you're done. If you're at the top of the ramp and it gives you the length of the ramp and the angle, you need to use trig to find the height. Having done that, I will pick my system as the Earth and the object. And then I recognize my free body diagram only has tension in the rope, but tension is perpendicular to displacement, so I know my work is 0. The other possibility is I could put the rope in the system. Now my free body diagram has no forces, so work is 0 because the external force is 0. And I'd have to make sure that as an internal object in my system, the rope doesn't do anything weird like add an energy or do something like that. So there is no, unfortunately, one right way to do these problems, as we have discovered with everything we've done this quarter. I prefer when there's a rope and the rope does no work as an external force, I like doing it that way. Then I don't have to worry about the rope anymore. It's outside the system. It's done no work. Now, we can make our little bars. We know the only thing we have is potential energy from gravity. We have some amount at the beginning. We have work is 0. Kinetic energy starts at 0 because I just let go. And then the final energy, there'll be some amount of kinetic and some amount of potential. And we can turn this into an equation. This was mgh initial equals 1/2 mv squared plus mgh final. This was at 45 degrees. This was at 30 degrees. And we already saw that h is L minus L cosine theta. So we have mg times L minus L cosine of 45 equals 1/2 mv squared plus mg times L minus L cosine of 30. And we were given L. Notice this is a great case where m cancels out. And if you plug in the numbers, which I'll leave to you to do, you should get v equals 2.5 meters per second. So on pause here, this is, like I said, except for the added step that we had to do trig to find h, this is about as easy as an energy conservation problem gets because you're given everything in your equation except the one unknown you want. I wanted the speed, and I found the speed with one equation, and I'm done. I just had to keep track and make sure there were no springs, there was no friction, so all I was left with those. I picked my system, I picked my h equals 0, and I was good to go, and I got my one equation. And I found v, my only unknown. Any questions on that? Yes? L is the length. I'm sorry. It was given in the problem. No, it wasn't given in the problem. I lied. I didn't type it. L is 2 meters. Sorry, when I post these, I'll recorrect the PowerPoint. That was a very good question. So let's try not to post the answer to the next clicker question here. Let's see what we can do. So let's suppose you're swinging a pendulum and the final angle is greater than the initial angle. In that situation, which of these are true? If the final angle is greater than the initial, you must be moving in the opposite direction because you've subtracted 2 cosines and it becomes negative. You can never have a final angle bigger than the initial because this violates energy conservation, or there must have been some initial speed, or none of the above. Good. Most people got it right. There must be some initial speed. And let's look at it in kind of an easier way. If all I'm dealing with is gravity, notice velocity, speed in this case, and energy is always squared, right? So let's suppose v final is 0. Then what this tells me right, is if h final was greater than h initial, there must have been some initial speed. That had to be positive. Notice if, in this case, if I know the final speed is 0, this is a case where h initial can't have been bigger than h final, because that would be telling me I'd have to take the square root of a negative number.
Would H final also be possibly greater than H initial if we had some outside work done?
Yes, I'm talking about a case where there's no other forces. I should have been clear in the question. Yeah, there are other ways to do it, like outside work, or if there'd been a spring in the problem, or other things like that. But in general, what I wanted to get at, v squared can never be less than 0. If you get that it was less than 0, either the question is asking you, could this have happened, in which case your answer is no, or you made a mistake. So those are the things you want to watch for. Any other questions on that? So let's look at kind of the next. This is long and wordy. Whoops. The next type of fairly straightforward problem. This is just kind of long because I've got to give you a lot of numbers. We've got a block. It's launched horizontally on a surface by a spring. That's almost the rest of this is numbers until you get to the question. How fast is it moving when it leaves the spring? And how far from its release point does it travel? Those are the two questions. Everything in here is numbers, that's information. But that's really, the first sentence is the physics, and the end is the question. And what we're looking at is a block that's going to move to x equals 0, where it will leave the spring, and then it'll travel some distance d. And I'll redraw that picture. But that's the fundamental problem that we're having. And again, the reason this is relatively straightforward is all we have to do is deal with a few of our energies. Right? So we have a spring. So we'll need the potential energy of the spring. We have friction. So we'll need to do our internal energy. And of course, we'll have kinetic energy. Notice if we pick, let me see, I think this is this a clicker question? Yeah. Let's pick our system. Go ahead and do that. So in this case, as I said, you can actually pick any of these. What will happen is, for some of the choices, you'll do work by certain forces, because you'll have external forces. For some of them, you won't do work. And some will be a little redundant. If I look at it, if I go back to my solution of the problem, right, if I pick as my system the block, the spring, and the floor, that's really all I need. Because, yes, in my free body diagram there is weight, but weight is perpendicular to delta x, so the work is still 0. I don't have to worry about it. If I put the Earth in my system, I would ask about any changes in potential energy, and I would see, oh wait, the height is always constant. There's no change in potential energy. So again, it wouldn't turn out to be relevant. So in this case, no matter which I do, I get the same result. I don't have to worry about gravity. The floor is kind of key because the floor is what's giving me friction. And I'd rather deal with that as an internal energy personally than work. Because otherwise you'd have to figure out the force of friction and do all of that. This one is a step up in complication because it's really, the question has broken it into two motions, motion A and motion B, right? What is our speed here is what it's asking. Notice, if all I asked was how far do I go, then this would be my initial, and this would be my final. And I wouldn't have to worry about what speed I had in the middle. The way to think about this with our bars, right, is if I consider this point 1, this point 2, and this point 3, there's never any work done, so I have the energy at 1 equals the energy at 2 equals the energy at 3. And initially, so I might have kinetic, potential energy from the spring, and energy dissipated. Right? And here, all I have is the spring. When I get to point 2, I don't have the spring anymore, but I'm moving and I dissipated some energy. When I'm done, all I've done is put everything into dissipated energy. And this will equal that. Because work equals 0 everywhere, so this initial equals this final. And if I started here, this initial equals this final. Or I can think of it as point 1 being the initial and that being the final. And this is what makes the energy problems sometimes slightly more complicated, is you will have two motions that you will connect using energy conservation. Now, what I want to do with this one, I'm going to leave this for you, okay, to work out the algebra for the two, but I will post a solution tonight, this afternoon, so you can look at it. Don't pack up yet. I've got a whole demo to do. We still got 5 minutes. Just because I'm leaving this for you to do doesn't mean we're out of time. Okay? So any questions on this one, though? Notice what I did. I'm just identifying which of my 4 energies I have. There's no potential energy from gravity, so I just have those 3. Now, let's go to the final one. Okay? Let's suppose I want to make a loop-de-loop. Ta-da! Okay, so real quickly vote. Suppose I want to ask, what height do I need to start my roller coaster so I just make it through the loop-de-loop? Real quickly as a review, you got 5 minutes on the clicker, no, 5 minutes, 3 seconds on the clicker question. What is the condition for the ball to just make it through the loop? It is not both A and B. It is not the velocity is 0. If the velocity is 0, we fall long before we get here. We fall somewhere over here. You just make it through when you just lose contact, and you just lose contact when the normal force is 0. Wait. Oh, yeah, we've still got like 3 minutes here. Okay? So what we have to do, if we want to figure out what's going on in this problem, right? The question was, how high do we have to start to just make it through? Notice we need some velocity here, because we need v squared over r acceleration. Velocity is in 1/2 mv squared. So we obviously have to start above here, and then we can make it through. If I start even would be a velocity of 0 there, right? Because mgh equals 1/2 mv squared plus mgh. This is the same height. Notice it fell off here. Okay? So this is a clear evidence that velocity equals 0 is not the condition for the top, but the normal force being 0. This is a problem that will be a bonus problem in discussion. So solve that other one and think about this.